Guess we should get started. Okay, so I was going to talk more about the stuff we talked about on Wednesday, which is finding equilibria, stability, instability. It seems worthwhile to cover again. And Parth, right, asked a very good question. For linear ones, like it seems kind of funky how you do. Well, linear ones are actually, if you think about it for a little bit, are some of the easiest cases to tell if it's stable or unstable. So in this example here, where x of t plus 1 equals negative 4x of t plus 3, right? That's a recursion. I'm not even going to find the equilibrium. Well, I'm going to, but I didn't find it yet. But if you look at this, these linear ones always have derivatives that are just always the same thing, right? Linear functions have constant derivatives. And so for this function here, negative 4x t plus 3, the derivative is just negative 4. And the absolute value of that is 4, which is always greater than 1. So no matter what equilibrium you find here, it's going to be unstable because the derivative at any point is going to be negative 4 and its absolute value is greater than 1. If you wanted to find, and then I start plugging in some values to kind of see like how it gets really, really big. Our equilibrium here, if we wanted to find it, would be, well, we'd set L equal to negative 4L plus 3. We'd add 4L to both sides. And we get L equal to 3/5. So if you plug in 3/5, you keep getting 3/5 back. But if you go even just slightly away from 3/5, like at 1, you start moving very, very far away from that value. And that's always kind of the hallmark of something that's unstable. Is if you, so what the language usually is if you perturb your equilibrium a little bit, if you move away from it a little bit, if you perturb it, if you're unstable, you're going to shoot way off. Whereas if you're stable, even if you move a little ways away from it, it'll push you back towards equilibrium. Yeah. And then in this other example, where x of t plus 1 equals negative 2/3 x of t plus 6, the derivative of that is going to be negative 2/3, which in absolute value is less than 1. And so here we have stability no matter what our equilibrium is. We can also find it setting L equal to negative 2/3 L plus 6. I would probably I'd probably multiply everything by 3 just because that seems not terrible. So 3L equals negative 2L plus 18. 5L equals 18. So L equals 18/5, or if you prefer, 3.6. And then for this one, if you started plugging in values, like let's say we started somewhere like 6. So if x sub 1 or x sub 0 equals 6, then x sub 1 is going to equal, if we plug in 6 here, negative 2/3 times 6 is, let's just do the math. That's going to be, let's see, negative 2/3 times 6 is negative 4 plus 6 is 2. And if you plug in 2, you're going to get negative 2/3 times 2 plus 6, which is going to be negative 4/3 plus 6, which is, I don't know, something, like negative 4/3 plus 18/3 is 14/3. And you keep going. The interesting thing about these stable ones, when you have a negative coefficient like this, or when the derivative is negative, is you get kind of this oscillating behavior where you go above and below. I think above and below, maybe not. Maybe we're not seeing that here specifically, but sometimes you get an oscillation from going below and above your stable point. Sometimes you just come at it from one direction or another. Let's look at a couple other examples that are not linear, because those ones are usually a little more challenging to solve for the stable equilibrium. Let's look at this example, which I changed it slightly. It's a little bit different. So let's say we have the following. Where'd you go? And so we want to write things so you can see them. Find and characterize all the equilibria for the following: x sub t plus 1 equal to, where'd you go? Sorry, a 7 x sub t squared over 10 plus x sub t squared. I was going to do a slightly different problem, and I was looking at the homework and realized it was exactly the same as the homework problem you guys already have. So this is very similar to problem 12 on guys' homework, in case you're curious. So first, we're going to find the equilibrium. So, thank you. Set all the x sub whatever is equal to L. So L equals 7L squared over 10 plus L squared. Multiply both sides by the denominator, so we're going to get 10L plus L cubed with 7L squared, and bring everything to the left. So L cubed minus 7L squared plus 10L equals 0. And then this should factor, and factor out an L, left of L squared minus 7L plus 10. And this factors further as L minus 5 times L minus 2. So our three equilibria are using like the notation of the book calls them X hat. Our X hat equal to 0, 2, and 5. So now we're going to go back. We're going to say, all right, our function f of x is that thing up there. 7x squared over 10 plus x squared. And we're going to take the derivative. I use the quotient rule. Let's see, it's the bottom times the derivative of the top, which is 14x, minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. And while I'm not always a fan of simplifying derivatives, I do think if we're going to be plugging in values here, it might make sense to simplify it a little bit. Also, there is something that simplifies fairly nicely here. So simplifying this, we get 140x plus 14x cubed minus 14x cubed. Oh, those cancel out. That's nice. All over 10 plus x squared squared. That seems worthwhile to me to do, to make it easier to plug in. So now let's try plugging in our various equilibria and see what we get. So plugging in 0, f prime of 0 is going to be 0, right? It's 140 times 0 over, it really doesn't matter at this point. Definitely 0. And I suppose you should write the opposite values, which is certainly less than 1. So it's definitely stable. And 0. All right, let's try another one. I like to write it without the opposite. So honestly, I really like doing it that way. I like writing the derivative and plugging it in and then getting a value, and then at the end, putting the opposite values around it so that I just don't like writing the opposite values as I go. So f prime of 2. I just started doing the thing I said I didn't want to do. Oh well. Is going to be, let's see, we're going to get 140 times 2 over 10 plus 2 squared squared. Okay, so the top is 280 and the bottom is 14 squared. What's bigger? 280 or 14 squared? I don't know 14 squared off the top of my head, but I do know 15 squared is 225. So 280 is definitely bigger than 14 squared, which means this is bigger than 1. I'm not sure. 14 squared is 196. I totally know what it is. But you can use numbers that are easier to figure out if you're not sure. Or you could actually just use a calculator, right, to figure out 14 squared is. But that's definitely bigger than 1, so it is unstable at this value. Let me finally, let's look at the third one. F prime of 5. So plugging in 5, 140 times 5 divided by 10 plus 5 squared squared. Okay, 140 times 5 is 700 times 10 divided by 2. And then 10 plus 5 squared is 20, and 20 squared is 400. So we also get instability there. I know everything here is already positive, but it's still good to be in the habit. Oops, I wrote 5 there. I should have written 2. Sorry. Just getting ready for the next problem too fast. I would imagine you'll see a question in this vein somewhere on your final, probably, right? This last homework assignment seems like there's a lot of questions like this. Seems pretty reasonable to assume or suppose there would be one like that on your final. As you go, I have more questions. Questions about this one? Yeah. Oh, did I make a mistake? Oh, yeah. Yeah, I totally made a mistake. Thank you. Don't let me get away with that. 10 plus, I made the mistake. I give my students a hard time for making that mistake. When you say 5 squared is 10, which is what I did. 5 squared is not 10, it's 35. Thank you. Okay. Darn it, I had all the room in the world, and now I don't. That's incorrect. It might still be unstable, but I don't think it is. So fine, we'll go do a new page here. So f prime of 5 is really 140 times 5 over 10 plus 25 squared, which is 700 over 35 squared. 35 squared is definitely bigger than 1,000. So this is definitely smaller than 1. Good catch. Thank you. So it's stable at x hat equal to 5. See, small errors can make a big difference. I will point out, if you were actually trying to like see what this value was without just knowing 35 squared is bigger than 1,000, there's a really easy simplification you could do here. 700 over 35 times 35. What's 700 divided by 35? What's 70 divided by 35? It's 20. It's 2. So this is going to be 20. And then, oh yeah, it's really obvious that 20 over 35 is definitely less than 1. That's another way you could have seen what that was bigger than or less than without having to whip out a calculator. All right, let's see, where was it there? Things all over the place here. Oh, there we go. So there's a couple other population growth models that you should see, and then they are present in your homework. One of them is the Logistic restricted growth model. Which looks like this. N sub t plus 1 is equal to n sub t times 1 plus r times 1 minus n sub t over k. And these numbers do have some meanings here. R is just a positive constant. And k is also a constant, but specifically k is called the carrying capacity. But it's still a constant. I think you have one like this in your homework where they give you a value of k, think of like 100, or maybe it's different for different people. Let's go ahead and actually just find the equilibria for this equation in general. So let's find the equilibria. So we're going to set n, the n's equal to L. So L equals L times 1 plus R times 1 minus L over K. And before we get going here, even though we don't need to say it, it should be pretty easy to see that L equal to 0 is an equilibrium. Right? If you plug in 0 here and 0 here, both sides are 0, great, it's an equilibrium. We'll see that when we solve it, but it's just kind of nice to make that observation. But I would bring everything to the right. So I would say 0 equals L times 1 plus R times 1 minus L over K minus L. And then I'd probably factor out an L. So 0 equals L times 1 plus R times 1 minus L over K minus 1. Oh, look, the ones cancel. That's nice. So then I've got 0 equal to L times R times 1 minus L over K. So either L can be 0 which is not very interesting, right? I mean, if you're talking about population growth, if you're starting with 0 animals or 0 whatevers, then you're saying that's stable. Well, it's kind of like duh, right? Of course, if you have 0 animals, you're not going to get more animals because they can't make more animals if you don't have any animals to make more animals. So this is kind of the trivial. Of course, that's listed an equilibrium. And then we also have, I didn't say, I almost said it was stable. I don't think it's actually stable. So we'll find out. And then over here, if we set 1 minus L over K equal to 0, we're going to end up getting L equal to K. And that is the carrying capacity. Can you see that? Meaning you can't go above K. So if you have a population that's somehow higher than K, it's going to get kind of pushed back down to B and K. It's kind of interesting. Let's look at an example with some numbers. Oh, no, it's more fun for you with numbers. I was going to say we could right now determine the stability, but actually it depends on R. So the stability or instability here totally depends on R. If you were to, no, let's not do that. No, using some fun paper. Okay. So let's look at the following example. Let's find and classify the equilibria when R equals 0.5 and K equals 200. So we could write out the formula. Not a bad idea. Right? N sub t plus 1 equals N sub t times 1 plus R is 0.5. And then we have 1 minus N sub t over 200. We already know what the equilibria are, though, based on what we just did. Right? The equilibria, which I'm going to call n hat. We usually call the equilibria the name of the variable with a hat. I don't know why I can swear a hat, but it does. What's one of my equilibrium? Equilibria? 0, definitely, for sure, 100%. And what's the other one? Well, look back here, right? We said the equilibrium were either 0 or K. So the other equilibrium is just n hat equal to 200. And if you really want, right, you can do a quick check. You can ask yourself, okay, if I plug in 0, do I get back 0? Well, of course I do, right? Plugging in 0, yeah, it's 0. The more interesting question is if I plug in 200, do I get back 200? So plug in 200, look what happens. I get 1 minus 200 over 200, that's going to be 0. And then I'm going to get 0 times 0.5 is still 0, plus 1 is 1 times 200. So yeah, when I plug in 200, all of this part goes away and you just get 200 times 1. So you get 200. Nice. So what about stability? So I'm going to rewrite my equation. I like to write it as a function of x. It just feels easiest to me. So I'm going to write this as f of x equal to x times 1 plus 0.5 times 1 minus x over 200. And while we certainly could use the product rule, it's probably going to be easier if we just multiply the whole thing out before we take the derivatives. So multiplying it out, let's multiply out this part first. So we've got x times 1 plus 1/2 times 1 is 1/2. 1/2 times x over 200 is x over 400. And then distributing the x, I get x times 1 plus 1/2 is 3/2. So I get 3/2 x minus x times x is x squared. That's going to be just a little bit nicer to differentiate, I think. Taking the derivative, we get 3/2 minus 2x over 400, which I guess we should simplify as 3/2 minus x over 200. And now we're going to check our points. If you plug in 0, you're going to get 3/2 minus 0, which is 3/2. And that is definitely bigger than 1. So it's unstable. Which hopefully makes sense, like biologically, right? If you have like 1 or 2 or like a small population, they're not going to tend back towards 0 usually in this sort of model, right? They're going to grow bigger and bigger and bigger. So usually 0 is an unstable when we talk about population things because populations don't typically move towards 0 if they're growing. And then we look at the other one, f prime of 200. Well, that's going to be 3 halves minus 200 over 200, which is 3 halves minus 1, which is 1 half. And again, that's the 1. So it's going to be stable. So kind of interestingly, if you start with values that are larger than 200, you're going to get pushed back down to 200. Start with values that are a little less than 200, you're going to get pushed up towards 200. Yeah, kind of all there is to say about that. Okay. Sorry, I'm like, questions, comments, concerns, observations. Welcome to the last day of the first quarter of fall 2021. Congratulations on making it through the first quarter. Just finals left. You can totally do it. Only finals. It's only a couple tests, maybe like 3 or 4. I know they feel like a big deal. You guys will be all right. You all will be all right. So let's look at, let's do one more. Also, there is I put on the table there an older practice review of sorts. Some of the problems might not be super applicable. So if you want to take that, feel free to work on them. If you think one is one you shouldn't do, don't do it. I'm also going to post the solutions on Canvas. So if you want to work through them, totally do that. But definitely there are some that are like, you probably are like, no, that doesn't seem very applicable. Just don't do them if you think they don't apply. Let's look at another population growth model. This one's called Ricker's curve, which I also think is making an appearance in your homework, if you're in Guy's class anyway. It's the only homework I can see. So the recursion is the population of t plus 1 is equal to the population of time t times e to the r times 1 minus nt over k. So here is an example of that. Suppose that the size of a fish population, any fish, at generation t is given by the following. N sub t plus 1 is equal to 1.5 times n sub t times e to the negative 0.001 times n sub t. And the same usual stuff. We're going to find the equilibrium and classify their stability, right? It's a little boring after a while, but it's good practice. So whenever you're trying to find the equilibrium, well, first of all, you're setting both things equal to L. Or I should say, you're setting all of your n sub t plus 1s and n sub t's, or x sub t plus 1, whatever your thing that's recurring is. Call that L, or whatever letter you like not n maybe. L. So 1.5 times L times e to the negative 0.001 times L. And almost every time, it's going to be a good idea to bring everything to one side. You totally could get away with dividing both sides by L if you remember that L has to be 0 as well. Right? Dividing by L means you miss out on the 0. So if you just remember that L should be 0 if you divide by L, that would totally be fine as well. But what I'm going to do is the safer method, which is I'm going to bring everything to one side. 0 equals 1.5 L e to the negative 0.001 L minus L. And then I'm going to factor out. I'm left with 1.5 e to the negative 0.001 L minus 1. But I think you can see we're going to get the same results as if you divided by L. If you divide by L, you get L equal to 0, and then you also get 1 equal to 1.5 e to the negative 0.001L, which is the same thing we're getting right here. So either way is okay as long as you're careful. Here, of course, we're going to get L equal to 0. You don't always get L equal to 0 as equilibrium, but you frequently do. So it's more likely than not going to be whenever equilibrium, whenever you're doing a problem like this. And here we have to do a little bit more work. We're going to set 1.5 e to the negative 0.001L equal to 1. We're going to divide both sides by 1.5, which is like multiplying both sides by 2/3. So e to the negative 0.001L equals 2/3. Then we're going to have to take the natural log of both sides. So negative 0.001L equals the natural log of 2/3. And finally, solving for L, you get that L is the natural log of 2/3 divided by negative 0.001, which is approximately 405. Okay. Now we do the derivative and we see if our things are stable or unstable. So let's see. Here's our function up here. We see that f of x is x times e to the, oh, sorry, it's not that one actually, apologies. It's that one there. F of x equals 1.5 times x times e to the negative 0.001 x. And then we're going to figure out what's going on with f prime of 0 and approximately f prime of 405. All right, so let's do it. I need my function to find my derivative. That's right there. So to find the derivative here, we're going to need to use the product rule. I typically, when I have a constant, when I have something like this where it's a constant times x times some other function, I kind of like to just think of this as one of my pieces. So when I take the derivative of this, I'm going to get the derivative of 1.5x, which is 1.5 times the other stuff, plus then the 1.5x times the derivative of this, which is going to be derivative e to the something is the same e to the something times the derivative of that something, which is negative 0.001. Now, we can definitely factor some stuff out here. I can for sure factor a 1.5 out and an e to the negative 0.001x, and I should. This is going to equal 1.5 times e to the negative 0.001x times 1 minus 0.001. Sorry, minus x times 0.001. So if I plug in 0, f prime of 0 is going to be 1.5 times e to the 0 times 1 minus 0, which is 1.5, which is bigger than 1. So unstable. And we're often not surprised by instability at 0. That usually that makes sense typically, because if you're a little bit away from 0, usually you don't tend back towards 0. Let's look at the other one. So I'm actually going to plug in the actual number. I have not the approximately 405, but my natural log of 2/3 over negative 0.001. So if I look at that, f prime of the natural log of 2/3 over negative 0.001. That was the previous value. Yeah. So plugging that in here, I'm going to get, all right, 1.5 times e to the negative 0.001 times natural log of 2/3 divided by negative 0.001. That's going to work out all right. Times, now we've got 1 minus the natural log of 2/3 over negative 0.001 times 0.001. Pretty gross, but it's going to be okay. So here's what we've got. These cancel. And what's e to the natural log of 2/3? 2/3. So that's going to be 1, right? 1.5 times 2/3 is 1. times 1 minus these cancel, except it changes the sign to 1 plus the natural log of 2/3. So this is right. So I end up getting 1 plus the natural log of 2/3. So are we stable or unstable? So don't get fooled. It looks like it's unstable because it looks like, if you're not careful, I was waiting for a second, like, oh no, it's unstable. I thought it was going to be stable. This seems like it'll be bigger than 1, but we have to remember that the natural log of 2/3 is actually negative. Right? If you think about the natural log graph, at 1 is where it goes from being negative to positive, right? The natural log graph has an intercept at 1, 0. So to the right of 1, the natural log graph is positive. To the left of 1, between 0 and 1, the natural log graph is negative. If it makes it easier, use a log rule. Natural log of 2/3 is the natural log of 2 minus the natural log of 3. Oh, that's for sure going to be negative. And 1 plus a negative number is less than 1. So this is actually, in fact, less than 1. Which is kind of cool. But right, easy to miss that if you're not thinking about it, because it looks like, oh, 1 plus something obviously is bigger than 1, unless the thing is negative, which it is. So we have stability at n hat approximately equal to 405. All right.